Hi, and welcome back to Hardware Design. So this is going to be the third part of looking at a uniform probability arbiter. So we're going to continue implementing this arbiter. We're taking a break from the rasterizer. So if you're one of the folks who's joining us after skipping a few, that's why we're talking about arbiters instead of the rasterizer. If we look in our notes, do we have notes for next time? We do. It says the thing that we have left for verification is testing out our fairness. So adding a new test vector and calculating some statistics. So the first thing we're going to do is I think we want to update our stimulus. So where's our excuse me, our random. So currently our driver model looks like this, but what we're interested in is doing something a little more complicated. There you go. So what we're interested in is the pattern that we've drawn above. So we're interested in having this sequence of sliding ones. And then more specifically, what we're going to try and do is we want the sequence of sliding ones, but shifting by one. So we actually want this to be a mask. So what we're actually going to do is we're going to write that A is equal to A and some mask. And then mask is going to be equal to mask 0. So we're going to shift the LSB up, and then we're going to shift everybody down 1. So that should be that guy. We've got our semicolon here. And then we just need to make sure that mask gets initialized. So misspelled mask here. So the only other thing we need to do is make sure that mask gets initialized somewhere. Do we have a good place to jam that? So we'll just do it up ahead here. So we want mask to be equal to, we'll say something like bit width. So some string of zeros plus 4HF. There we go. So what that'll do is that'll initialize mask so that the bottom 4 bits are 1. Good. So let's see. So let's not trust that our code works right off the bat. So let's run a little test. So when we can do these really fast checks to make sure that our code's working, we should do that. Looks like the stream cut out at some point and cut back in. Hopefully that gets stitched up later. So it looks like we have a syntax error here. The issue is that we didn't close the begin beforehand. So you need, if you have a begin, you need an end. We had initial begin but no ends because we just want to run this one line at the very beginning. Mask has not been declared yet. Oh, good. So we'll add that to our list. Good. So we're just compiling to make sure that it's running the way we expect. And it is not. So it seems like mask is held constant and isn't getting updated. And the issue is that this 0 needs to be a 1. So that should give us the shifting property. Great. And so it looks like we have this sort of spiraling random ones. You know, sometimes you have 3, sometimes you just have 1. Sometimes you get all 4, but it's always in this sliding window. Perfect, 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 perfect. So now that that's done, so that is our test pattern now. The next thing we would like to do is that we need to test the statistics. So the way we've defined fairness for this arbiter is that in the aggregate, if there should be a uniform probability of winning. So the idea is that if I'm looking at this highlighted vector, there's a 1/4 probability that each will win. So we could say the expectation of winning for each of these is 1/4. And what we would like is that the sum of expectations closely matches the number of actual wins. So what that means is that we'll need to keep track of who has won. So what we so let's see. So we will do always at pause edge clock begin end. So we're actually interested in neg edge clock plus 10. So why are we testing at neg edge clock plus 10? So what we're going to do is we're summing up. So what I'm a little bit worried about is that if I wait until after the positive edge, the displayed win will be the win that results from making. So let's see what's a. So if we bring up our uniform arbiter, what will happen is that at the negative edge of the clock, we'll propagate a new input in, so a new input A, and that'll propagate through, and that'll be the winner for that positive edge. Now at the end of that positive edge, we're going to store that value, and so that'll be into the last winner register. And so from the positive edge of the clock to the negative edge of the clock, what's happening is that the input is still last cycle's input, and we're using last cycle's winner. So if we look, you know, if we actually count that winner instead of the other winner, we run into a problem. This test is also a little bit broken. You know, maybe we should make this like neg edge plus 10 too. This worked pretty. This was fine because as long as the state was updating, you know, it would always produce the same output. But we'll update that just to be the same. So yeah, so hopefully that makes sense. If it didn't quite, you know, feel free to ask questions along the way, or post in the subreddit the Reddit post that we have going for this. Okay, so that was that. And so what we're interested in is keeping track of the number of winners. All right, so what we'll do is for my dollar A, so we're going to loop over all of the possible folks, $BW, $A plus plus. So we're gonna iterate over all of the possible winners. And then we'll say something like, okay, well, win numerator should be equal to So we'll say that, you know, there's a win count, and that win count is indexed on, you know, $A. Is going to be equal to a win on A. And, you know, we could write this more elegantly as, you know, $A. Right, so if Z doesn't win, we'll just be adding 0, but if it does win, we'll add 1. And then we can do win, you know, bid count for I, you know, $A. So this is the number of times that it bids, and that's going to be equal to A tick $A tick that. So now we have that bid count. So now so this is, you know, count actual wins, count actual bids, and then what we're interested in is the expectation of the win. And then in order to count the expectation, we actually need the pop count. And so we're going to do that in, you know, pop count equals bids 0. So we need to know what the base probability was. And so the way we do that is just counting the number of ones, because if it's uniform, that's the numerator in the expectation. Then we can do the same trick. You know, we'll count from A, but we should start at 1. Great. So now we have a count of the total wins. And then, so then the expectation is going to be the I2R of, you know, we'll say something like 5D0. You know, so we'll make like a 6-bit number here. The A $I. Should have picked a better variable than A for my index. Okay, so we're going to convert the integer to a real, so that's what I2R does. So if this is 1, it'll turn into 1.0. If it's 0, it'll turn to 0.0. And then we're going to divide it by the pop count. Great. And so that is the number. Now, we're going to run into a weird case where if pop count is greater than, if pop count is 0, and this will happen every now and then. I don't know that we have an example here, but every now and then pop count will be 0, and so we shouldn't do anything. And so let's help ourselves out. Pop count greater than 0, then do that. You know, otherwise 0.0. Great. Easy enough. We should probably define a few things. Or we should initialize these values. So we should set these equal to 0 at the beginning. So these are integers, but this was floating point. Good. And then the one thing that we forgot here is that during reset, this will behave in a very interesting way, right? Because the last winner will always be 0. So we're just going to guard this to prevent anything from updating it when we're not in reset. And then as soon as we're out of reset, we should be fine. All right. So let's make sure that we're good. Okay, so I think that is those guys. So then we need to declare some signals. So I think we have pop count as an integer. We have int win count that is bw minus 1 to 0. Bit count, and then we have the expectation of wins, and then this isn't int, this is real. So that should be that. And then the last thing that we want to do is that we want to display our statistics. So how we're going to do that is we're going to use this final begin environment. And so we're, for my $A equals 0, $A less than bit width, $A plus plus, we'll display wins versus expectation for $A, and we'll do it as floating point numbers. So the first one should be wins, the other one should be that, and then we'll display the $I to R of win count at $A. And what did we call the other one? The other one was, I think, expected wins, EXP win, yeah. Take $A. Good. And if we're feeling good, if we are happy, we will add tests. So the idea would be we'll set some metric and see if we can't hit it. Great, 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 great. So we hit some error. So it looks like line 160. There's some weirdness going on. Syntax error at line 160. Ooh, so that's not fun. So it looks like we've done something. So we're probably missing a right curly brace, is what it's telling us. That we forgot to close out one of our for loops. So we just added a whole bunch of for loops. So it looks like we've screwed up that one. bids have not been declared yet. That's right. So we didn't call it bids in this design. We called it A in this design. Okay. So we're running. All right. So, 63, 64, that's pretty good. 51, 50, that's good. 57, 65, that's really bad. So that's probably way off. 51, 48, 56, 60. But these are pretty small numbers to begin with. You can see that we have fractions here. So yeah, so it's not clear that, and so certainly I don't think we have any errors. So we can look through the logs. Yeah, so there's nothing wrong in the logs. So one of the questions is this bad? Is this bad because we've only done a small number of tests, or is this bad because we need to do more? So what we'll do is, we just deleted some of that text, so that'll make this less verbose. And then what we should do is we should try and normalize our answers. So we'll normalize our answers with bid count. And we're going to comment out this code. So we're commenting out that print statement, and then we're gonna use bid count to help us out. So that should normalize our answers, hopefully. Yep. So now they're more normalized. So that now we have these nice decimals in that place. So what we're worried about is how close are they? So maybe what we'll do is we'll sort of go let's I less than take $BW I plus plus. Okay. And then we'll say that so we need a test that sort of says the difference between those two things should be small. So what we want to say is the error is going to be equal to the difference of those two numbers. So we'll just subtract. My cursor doesn't appear to want to work. Interesting. There we go. So the difference of those two numbers, we'll put some parens around this one as well. So that's the error. Line's a little long. So we'll say then we need to change these i's. So let's make our life easier by just saying that it's error times error. And I'm thinking that we forgot to close a paren up here is the reason that that's giving us some trouble. Okay, great. And then we'll assert that square error is less than 0.0 0.01. Sure, why not? Else $display %d I. Bit I is unfair. Okay. So that'll. So now we should run that. That should fail left and right because the differences between these things is small. And we have signals that just haven't been declared yet. So there is that. It's going to complain at us because we didn't name the assertion. And it's going to go, okay, well, it's not fair. This is roughly why that's happening. So but did all of them fail? So 1, 5, 6, 8, 9, 12, and 14 failed. So 14 is unfair. Did we just not add the is? Yeah, there we go. Is unfair. Okay. So so now we're just worried about is this running long enough? So let's add two zeros to our runtime. So now this will run a little bit longer. Well, a lot of bit longer. But not too much, and we've certainly come out fair on the other side. All right, so and then I think we said when we started that we were shooting for like with 1%. So since it's the square, that would be one more zero there. How did we do? And it really does not like the unnamed assertion. So okay, so that one more zero was just asking for too much. That's right. So they still differ in the thousands place. I mean in the hundreds place, a fair number of them, which is why we were we got away with that. So we're not quite 1 in 10 fair. That could just be simulation noise, so we could add that back and add one more zero. See if we get a little bit closer. This is one of the problems with more statistically oriented things is that eventually you start having to do a larger number of runs. So now we're cooking, and we're still not fair. The numbers are still a little bit off. Some are a little bit higher, some are a little bit lower, but for the most part we're almost the 4.8, the 4.75 that I think the number's supposed to be. And it's not all the bits, it's just 0, 1, 8, 9, 14, and 15, so it seems like most of them are pretty close. Is there a way to change the bit width? Bum, 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 bum. So I hard-coded it to 16 everywhere. Okay. So I think the one we built, it's not perfect, but we're certainly You know, what if we make this a 5? You know, do we squeak by? Yeah, so we almost sneaked by. So there were a few that just were not quite there. So 0 missed out, and 9 missed out. Yeah, 9 was a good bit off. Is that it? You know, it was roughly 49% of bids were won in reality, but the expectation was 46 out of 100. So, but yeah, most of them are pretty close. So I you know, this should certainly be enough for me to claim victory, and say this is fairly reasonable. And this is almost a textbook implementation of a round robin arbiter. It differs a little bit from the Wikipedia definition. I think the Wikipedia one still says that the shift is always constant, whereas the textbooks sort of say that it's always this trick of shift so that the winner, the last cycle's winner, is the lowest priority in the current cycle. So that's about it for this. I think we can kind of call that. One of the things that we might do, if we were kind of interested in you know, taking this a step further, is that there are other measures of fairness. So one of them is, you know, so I think we sort of measured the uniform probability. We assumed everybody was independent, but another measure would be how long a bid sat. Did a bid have to wait for a resource? Because certainly one of the things that the statistics we're using and the simulation we're using would hide is it could take almost 16 cycles for somebody to get a turn. We're not totally sure if that's true. Part of the problem is that our vector, the way we generate our test pattern, is that we're always doing a brand new vector that's shifted a little bit. So what we could do is we could preserve that vector, shift it a little bit, and then statistically add one bid per cycle. You know, so some cycles there's 2, some cycles there's none, and then we'd want to see that, you know, on average it didn't have to wait too long. And then depending on the statistics that we have, like how bursty it is versus the uniformness, you know, might determine how effective the hardware is at dealing with these things. And certainly if you were building something that was trying to minimize the wait time, we might actually want to build a counter for each bit slice and then prioritize them based off of that count. Is to set priority based off of who's waited the longest, and then have some cleverness to provide a fairness in those cases, because you certainly don't want, in cases where everybody's waited the same amount of time, to always let the most significant bit win or the least significant bit win. So you might want to combine this with multiple schemes. So there's a lot that can happen with arbiters that's fun. We will pick up with a new hardware design next time, now that we've more or less verified this or and got it up and running. If there's designs that you would like to see, you know, feel free to post in the comments for the video. There's a subreddit. So I think I've been posting under the subreddit for ECE. Yeah. Yep. So if you look for hardware design in the ECE subreddit, there's a post that points to this YouTube video. That's another place to discuss. Or I think I tweet about this, so you could tweet at me, and you know, all those would work as well. If you're a student in my class, you know, feel free to just mention it in class or an email. I'm happy to take a look at that. Otherwise, have a great week, and I will see you all next time.